Okay, so hello after the afternoon. So yesterday we talked about the de geometry, and sort of our main discussion was based on coordinate systems and and drawing the Penrose diagram, which made us see that in de Sitter spacetime there exist two physical boundaries. And these boundaries lie along the time direction. So there is one late time boundary at future times and one early time boundary in the far past. So today we will talk about, and yesterday I said was GR friendly, and today I said it was going to be quantum field theory like the discussion. So today we will focus on symmetries. Now, if you open up a standard textbook on quantum field theory, its goal is to discuss elementary particles. And this is set up on Minkowski spacetime. And you develop all these technologies associated with S-matrix methods, computing, scattering amplitudes, these kind of physical processes. And if you think of it, the scales these interactions happen are quite nearby, closed scales compared to the whole universe. So even if we live on a curved universe, it doesn't matter at the scale of particle interactions, it looks flat. But when you start talking about the evolution of the universe, then you need to take the curvature into account. And so maybe not all of the techniques we learn for particle physics carry on to cosmology, but just because the geometry is different. But so if we look at it from the point of view, what is the general message that we can take and sort of study how it specializes from one geometry to another? This would be what Wigner brought forth around 1939. He introduced the notion to think of elementary particles as unitary irreducible representations of the Poincare group. So the message, so in here, the Poincare group arises because we're studying particles on Minkowski spacetime, on flat spacetime, and Poincare group is the isometry group of Minkowski. Now, what this group needs to be, like what group you need to focus on, may change depending on the geometry you are considering. So, for instance, in our story, it's not Minkowski, but the spacetime is de Sitter. So we kind of need to go back and think on what's the isometry group in this case. But the main message that stays is to focus on unitary irreducible representations to understand the physics of the situation. So maybe you don't have S-matrix methods in this case for some technical reasons, but you know, you look at the representations and you think what questions you can ask using these representations, like what do these symmetries at hand? Okay, what kind of questions the symmetries at hand allow you to ask? So it's even an education to learn to ask appropriate questions. So that's the first thing to say. Let's change our color. Now, what are these representations? Unitarity, the unitarity property of a representation means it leads to normalizable states. For the representations. Now, unitarity of interactions is a different subject. So just don't be focused about that. Here we will consider, here we will talk about representations. Irreducible means these are like the elementary pieces of a puzzle. You can put them together, but you cannot break them down into further smaller objects. So let's say the smallest pieces. Of course, these are all mathematical definitions. And so you can, like the definitions I give you are a little bit intuitive, but to work with it, to check that a representation is irreducible, all of these things, you need to use a lot of mathematical structure. So for that, anytime you are doing this, it's best to consult a piece of mathematical literature. So don't forget to look up these definitions from some group theory book. Like if you want to make a calculation, you will need to make use of that. And I will tell you some books, and I will give you a list of some books as well, but you can also just look at any one of your favorite book. But now let's go back to this group. So I said in the case of particle physics, this is set up on flat space-time on Minkowski. And so the group that arises is the Poincare group because this is the isometric group of Minkowski. What this means, considering unitary irreducible representations of the Poincare group, means you label particles by mass and spin. So from a priori, like you don't know how to designate, what to say to designate a particle, but all these, looking at the properties of the representation, also tells you that. And in the case of the Poincare group, this happens to be the mass and spin. But now, what does it mean? What does an isometry group mean? This is isometries are coordinate transformations that leave the metric invariant. Now, what precisely these transformations are changes from metric to metric. It depends on what metric you are working with. So our goal is for this lecture, is to find the isometric group for de Sitter spacetime. But to begin with, let's just focus on two-dimensional Euclidean space. So this is like the surface of your table, just flat space, because it will be faster to work out what these are, and it will be a good demonstration to carry on in a short time. Now, this is the metric on Euclidean space in 2 dimensions. So we just have 2 coordinates, and we can define position vectors like this, if you like, with an X and a Y coordinate. So this metric is the length of the smallest distance. So the smallest distance would be like this. Okay, so this metric is just that. Now, what are the transformations I can do on the coordinates that will not change this? The first thing is, by definition, rotations preserve lengths. So I can take this, so on 2 dimensions. I can just rotate this plane by some angle. The coordinates will change. So if I am looking at the distance between 2 points, the coordinates of these points will change, but the distance between them will not change. So if you want, you can designate these transformations by a finite dimensional matrix R. So it would be 2 by 2 in this case. And this would be an orthogonal matrix. That means its transpose would be its inverse. And this is what lets it keep the distances, the lengths preserved. So this is the first isometry is rotations. Second, notice that if I move my coordinates by a fixed amount, like shift them to the right or up or something like this. So if I let x go to x plus a, the distance between 2 points along the x direction will not change. I can also do this along the y direction by some other amount. So these are called translations. So if you want this, if this is x tilde, the x is the same as the x tilde. So these kind of transformations. Now we found 2 symmetries. Here, 2 types of symmetries. Here we are rotating our surface around the direction perpendicular to the surface. So we can parameterize these by an angle, theta. But I mean, there's just, there's just one plane to rotate around for this. So there's just one rotation around an axis perpendicular to the plane. And then we can, so we have 2 directions. We can translate along each one of them. So we have 2 translations. One along the x direction and another one along the y direction. Okay, so we found 3, but is this all? You might ask. And here we could just look and guess these because the metric was very simple. Now, a more educated, for sure, way of doing this is to consult to what is called the Killing's equation. So it's this equation. And this is an equation based on your geometry, because for a given, so this, notice that here, these nablas are the covariant derivatives. So this is based on geometry at hand. And you solve this equation for the, solve the equation for these psi mu's, the components of the Killing vector. This gives you all the isometries, all the coordinate transformations that keep a metric invariant. Now, if you've just taken a GR course, you may or may not have encountered this equation, but in Volt, there is a nice appendix on this. And if you wanted to do some exercises, you can try to find the Killing vectors for some geometries. For Minkowski, this covariant, I mean, because there is no curvature, this covariant derivative is just the normal partial derivative. So you end up with an equation like this that is quite easy to solve. One immediate solution is if, okay, so we have 2 coordinates. So for R2, for Minkowski for Rn, for these it's easy. So for R2, we just have 2 coordinates, there's 0 and 1. So what this equation can be is, okay, you keep picking. So you can set, let's see how to, you can set mu equals 1. There's 2 of these, so never mind. You can set mu equals 0. And you can take mu equals 0, mu equals 1. Or the other way around. But it's basically the same equation. So to find the killing vectors of R2, you have to simultaneously solve these 3 equations, and you will get so altogether this vector is like this. But because we're on flat space, it's just easy to raise and lower indices, so it doesn't matter. And these components need to solve each one of these equations. So they need to solve these equations simultaneously. So we have, okay. Now, one immediate solution is to have equals 1. Like every individual piece 0. This just means something constant. Okay, maybe 0 and 1 is not very good because we were using 0 for time direction, and here we only have spatial directions. So let's just make these 2 and 1. So this is a vector like ax del x, ay. Del y. This is one killing vector. And notice that this is just shifting everything by a constant amount. So this is just translations. You could have set 1, like you can ax, ay are constants. You can have just ax del x. It will still solve all these equations simultaneously. So this you can split into 2 independent pieces. So there's an x translation and a y translation. If you look at it a little, if you try to work with it a little bit more, you'll find one more solution, a different solution that's like this. And this is the one that generates rotations. Now, these, and these are all the isometries. Well, there is one more, but maybe you saw it, but you did not mention it, but just wait a little bit. Now, we are, so these ax, ays are some parameters, and they can take on any value, right? Like you can translate by any amount. It can be something where like you can translate by 5 units, you can translate by 0.1 units. So these ax, ay can be anything. They're continuous. Rotations, it's also the same. You can translate by any little angle. Okay, maybe not to write it like this, but any infinitesimal amount. Can be any number. So rotations also, you can have very tiny infinitesimal rotations. So you sweep through all possible angles. So this is parameterized by an angle. In this case, we have one rotation, so we only have one angle. It could have been more angles in more dimensions, but this is also a continuous parameter. These are continuous transformations. There is one more. Yes. We could have also reflected all the directions. So we could have sent x to minus x, y to minus y. This would have just given us an overall minus in the metric. Well, actually it gives an overall minus, so it's not even a symmetry transformation. But just in case, if there was a metric that had this as its symmetry, this would have been a discrete, because this is a discrete transformation, this would have been a discrete symmetry. Now, so there is this difference. We talked about transformations. These transformations can be maybe parameterized in some way, and you split them into different categories depending on that parameter being continuous or discrete. So this is the first thing to notice. So continuous transformations versus discrete transformations. Okay. Now, of all these transformations we found, notice that, so let's go like this, rotations and translations. In all these transformations, there is a transformation that does nothing. So that's the unit operation. So you can rotate by 0 angles, 0 degrees, and you can translate by 0 amounts. This does nothing. So you can always find the unit transformation. And then there is also inverse transformations. You can, so say you rotate it by theta. You can reverse this by rotating an amount minus theta. So you can rotate in the opposite direction back and go back to where you started from. You can translate by A and then reverse this by translating by minus A. So you can always translate and then go back. So there's these inverse versions of all these transformations we are talking about. And another thing, if you rotate twice, so rotate theta 1, then rotate theta 2, altogether this is one rotation on its own, in the same, we're rotating in the same direction. This is the same as another rotation, which would have had the parameter, whatever these two angles added up to. The same goes for translations. So you can translate by A, then on top of it, translate in the same direction by B. This is, okay, let's copy BX. This is the same as having done one bigger translation. So just so you can do 2 transformations along the same direction back to back, and that itself is like whatever the category of the original translation was. It's just the same translation by a different parameter. So you can do more of these, 2, 3 of these. And the order matters, but you can group these differently. So you can first consider this as one transformation. So call this G1, 2. And then you look at to put the third transformation on top of this compound. Or you can just consider having started with this G1 transformation, whatever it was, and then apply on top of it the compound G2, 3 translation. The order is not changing, but the way you are breaking that huge transformation into smaller sub-translations is changing. And so this structure applies when you talk about rotations along the same direction or translations along the same direction. Now, operations, so a set of elements with some operation on them that satisfies all these three properties. Satisfies these properties is called a group. And we just saw that, we just discussed that our transformations satisfy all these properties. So actually our translations plus rotations, these also form a group. And because these are, these being the transformations that leave the metric of R2 invariant, this is called the isometry group. Anyway, iso has something to do with being same as a word as well. So this is what, if we go back, we said the Poincare group was the isometry group of Minkowski. It means it has all the transformations that leave the Minkowski metric invariant, and all of those transformations all together form a group. Okay, so here, for instance, we considered the isometry group of two-dimensional Euclidean space, and we saw that it's composed of translations and rotations. Now, this other transformation we talked about, this wasn't this reflections, for example, this wasn't a symmetry of the Euclidean space, but it can be the symmetry of some other system. But notice that this was discrete. This had discrete parameters. So there is this distinction between you can have continuous groups with continuous parameters. This will have an infinite number of elements, because think of translations. For each translation parameter, you have a group element, and you can translate from 0 to infinity, infinite amounts of parameters, so infinite amounts of group elements. But then there's another category, finite groups. I guess you can also call them discrete groups. These have discrete parameters. If you like, the reflection in some sense is rotations with parameter theta equals 0 and theta equals pi. So just two elements. So these kind of groups have a finite number of parameters. Now, if this is your very first introduction to group theory, I suggest there's a book by Wigner. It's called Group Theory and its Applications in Atomic Spectra. And it starts by talking about rotations, translations. It talks about finite groups, continuous groups, and it does everything. I mean, you will see situations you are familiar with in classical mechanics in terms of rotations, all these Euler angle things, and situations you are familiar with from quantum mechanics when you study spin or angular momentum. You will see all of that re-explained in this language. So this would be very introductory. Then a little bit more advanced, there is a Feyza-Gürsey, Lezouche lecture notes. Remember, Lezouche was an important school. That happens, I guess, once a year. I think it still continues, a bit more advanced. This is okay, so I told you I'm making a list of references, so this will be in that list. You just need to find which year it is from. These set of lecture notes, so all, like all the lecture notes from the school. So this Feyza-Gürsey's notes are just one section of it. They're a little bit hard to find online, but you can manage to find it. But if you find that edition, so all the lectures from which this Feyza-Gürsey lectures were part of, they are all on subjects that set the basics of some important discussions even today. Like there's a lot of lecture notes that set the basics of gravitational radiation, for example. So like if you happen to find this version of Lezouche notes, it seems like a good source to have. But okay, so we saw that these two distinctions, there is continuous groups and finite groups. Now, what's special for continuous groups? If you have these continuous amount of parameters, you can talk about infinitesimal amount of differences from one group element to the other. So you can talk about group elements being infinitesimally close to each other. This means you can also talk about group elements being infinitesimally close to the identity. So remember what the identity was. This was the don't do anything, or you have done nothing. You haven't changed anything operation. Now, what this means is it doesn't mean all the elements are right next to the identity. It means wherever this identity element is, and like your group has all these elements everywhere, you can talk about a set of elements close to the identity. In a sense, you start thinking about group elements as if they are coordinates, because they're so next to each other. So you can just analyze the group's properties by analyzing whatever happens next to the identity. This also means, because you can have these infinitesimal changes and you have continuous parameters, so the group element can be denoted as functions of these parameters. you can have the notion of differentiation with respect to the parameters. So this is something defined. And then you can do things like Taylor expansion. You can Taylor expand group elements around the identity. So there will be, let's see, so the identity will happen at a specific value. So if you are talking about rotations, this is, identity is at the angle equals 0. The parameter, that is angle of the rotation, equals 0. Like this. Then you make use of this to represent what this leads to. You can okay, let me first define one more thing. So I said this differentiation exists. So you can have higher derivatives g to all of this. This first order derivative evaluated at the value of the parameter that gives you the unit element is called the generator. It's denoted by chi. Okay. There is a convention in physics literature. We like to define it with an overall I being this square root of -1. In mathematics literature, you define it without this I. It's a convention in definition. It just means something about the generators being Hermitian or skew Hermitian for unitary operators, if they're to define unitary operators. But so there's this one in physics definition, physics literature. And that's just no such factor in math literature. But so you can then define, you can realize group elements or represent by exponential maps of the generator. So this is really multiplication. Okay. Now, and yes, what all this means is you can analyze everything by analyzing, you can analyze the whole group by analyzing what happens around the identity. Now, such groups are called Lie groups, so groups with continuous parameters. Continuous groups. Now we said the elements of a group satisfy a closed operation with all these properties we mentioned in the beginning. This existence of inverse, existence of unit element, and this association law. Now for Lie groups, furthermore, so there exist generators, and these generators also satisfy something. They satisfy a closed algebra. So actually, like yesterday, you started seeing Grassmann algebra. So, you know, that's one example of an algebra. Now, this is an example of a different algebra. So what this algebra does is, so if you take some elements of the algebra and some scalar quantities. So this means these commutators don't do anything to these scalar quantities. So there is this linear relationship. If you take the commutator of a generator with itself, it will give you 0. And there is this cyclic property. So this is called the Jacobi identity. You see the 1, 2, 3 keep changing in a cyclic manner. This needs to be satisfied. And if you reverse the order of the entries, you just get an overall minus. So this is the properties of the algebra. And this algebra is called the Lie algebra. So for every Lie group, there is also this Lie algebra. So it governs the structure, the properties of the generators. And the generators are useful because you can talk about building representations of them. But now with all this information, let's go back to the symmetries of R2. We found that these involve rotations and translations. Now we saw that both of these have continuous parameters. They satisfy group axioms. So those 3 things written in light blue in the beginning that made us say that we checked and we said, okay, they satisfy these, so these form groups. And so having continuous parameters there and having a unit element, the elements are continuously connected to the identity. So these are also Lie groups, examples of Lie groups, or belong to Lie group category. Okay. Now, this Lie group has a name. Let's change colors. This is ISO plus 2. I think you can also see it denoted by E2, E for Euclidean. Now, what does this naming mean? O stands for orthogonal. This means these group elements, because of this 2, are 2 by 2 orthogonal matrices. S stands for special, but the specialness of it is the determinant equals to 1. So this bit makes rotations. I stands for inhomogeneous. It means on top of rotations, there's also translations. As well as rotations. This plus sign denotes that the group elements are continuously connected to the identity. So in practice for this group, it means you don't have reflections. Another group would be without this plus. So this would be ISO2. This would be all of this and the reflections involved as well. But usually in a lot of textbooks, they just drop out the plus just for convenience. And somewhere in the beginning, they say, we will write ISO2, but it means we are considering elements connected to the identity. So we don't have reflections. Okay, so also from now on, we will just, well, we will not talk about this too much, but we will drop the label, drop the plus below as convention. We may, okay. And so all of this, these group elements define transformations that leave the distance on Euclidean space invariant. So if you like this. Now, within SO2, actually translations on their own form a group and rotations on their own form a group. So these are subgroups. I mean, this is pretty much like dividing a set into its subsets. A group can have subgroups, but what those subgroups are, again, depends on the group. And so you can also say the technical term for this is this group ISO2 is the direct product of translations and rotations. Now, this being a Lie group also has a Lie algebra, and usually the algebra is denoted by lowercase lettered version of however the group was denoted. So these smaller lowercase letters, ISO2, denote the Lie algebra of the Lie group ISO2. I feel like you can keep thinking of these. What this means
Gizem hocam bir şey sorabilir miyim? Burada 2 dışında 3 desek mesela 3'e 3'lük bir matris şeklinde temsil edebilir miydik? Yoksa sadece iyi mi temsil edebiliyor? Yani vektör uzaylarını sadece bu 2 boyutlu vektör uzaylarını da mı temsil ediyor?
Her boyuta genelleştirilebilir. Biz 2 boyutlu bir şeyin simetrilerini bulduğumuz için böyle ikili bir grup bulduk. Bu da 2 ikilik temsil oldu. Let's like this. More generally, this is a group SO and it will have group elements will be n by n matrices with unit determinant. So if you look at, you can do, actually a good exercise. Write down the metric on 3-dimensional Euclidean space. Try to find its symmetries. You will find translations along 3 directions, not just 2, like X, Y, Z. And you will find 3 rotations, each along 1 direction. So that will be a bigger group because it will have more elements, but the nature of the group will be quite similar to this. And then you will see, like, if you open up some book and look at its group elements as written down as matrices, or if you calculate this yourself, you will see 3 by 3 matrices if you look at ISO3. Okay? So
bir de burada hocam şey yok, reflection yok zannedersem. Değil mi?
No reflection, evet, onu çünkü birim elemanı bağlı yani birim elemanı da grup elemanlarımız birim elemana bağlı kalsın istediğimiz için. Yani, ama zaten metriğin bir simetrisi de değil. Yani metriği değiştirmiyor. Metriğin başına bir eksi getiriyor.
Reflection olduğu zaman grup olma özelliğini kaybediyor mu yoksa sadece?
Hayır. Okay. So the group ISOM plus without reflections is one group. Okay. ISON with reflections is another. But this one is not the isometry group. This one is the isometry group. Happens to be the isometry group. Okay, let's go back to our two-dimensional example because we calculated it explicitly, so we know of R2. Because reflections gave an overall minus sign. Reflections on their own are a group, and that's in fact, that's the first group you come across because it's the simplest. It just have two elements, identity and something else that if you do it twice, you get back to where you were. So that is a group too. So there's a lot of groups, but they don't all have to appear in a physical question or for our question of interest, that is not the group. For our question of interest, the group that involves reflections is not the group we need. Okay, so about this Lie algebra. So this Lie algebra, you can write it down by computing commutators of the killing vectors we found. So we had translations along X, we had rotations along Y, and we had, translations along Y, and we had rotations. And these are all like differential operators, right? Now, in 2 dimensions, there's only one rotation, just one rotation are perpendicular to the path. One rotation around the axis perpendicular to the plane. So automatically this is going to commute itself. I mean, the only commutator you can compute for in terms of rotations is just this one rotation killing vector. Now, as opposed to, so this automatically commutes itself, and such objects that commute are called abelian. Like in this algebra of just rotations, so this is just the SO2 algebra, not the inhomogeneous part, we only have one generator. So this is the full SO2 algebra. These are small letters. So this SO2 algebra is abelian. You can look at like at the level of group elements also, it will commute. It doesn't matter when you rotate back and front, like, you know, the order doesn't matter if there is just one direction. So this is abelian. But if you go into higher dimensions, you have more generators and you have more group elements. I mean, kinds of group elements. So you have more versions of parameters, like angles for different directions. And if you compute their algebra, it gets a little bit more involved. So it's not just abelian. This will be non-abelian. So things won't all just commute. And if you do this, if you compute these, so if you compute things like Z rotation with Y rotation, you will find something more. What you find happens to be like with a plus or minus. And this will be proportional to the X rotation. So you get an algebra that resembles the algebra of angular momentum. And you can also do this for translations. You find that it resembles the algebra for linear momentum. And so actually this is why maybe you heard this sentence, but looking at the generators and the algebra they satisfy, you can recognize translation generators to be linear momentum operators and rotation generals to be angular momentum operators. So we were talking about mathematical objects, but there's a physical connection to physical objects from them. Now we split, so we said groups. We said we split them into finite groups with a finite number of elements and discrete parameters, and continuous groups with infinite number of elements with continuous parameters. There is one more categorization. Now, consider the parameters of rotations. These are angles, and these vary in a finite range. Moreover, theta equals 0 is the same as theta equals 2 pi. So it's like it's a finite range that goes back to where you started from. Groups whose parameters are like this, lie in a finite range, are called compact groups. And if you consider translations, we said you can translate by any amount. So these values of translation parameter lie along the real axis. So this is an infinite range. So groups whose parameters lie along an infinite range are called non-compact. This is one more categorization. Now, unitary irreducible representations. So this is unitary irreducible representations. Have differences, whether they belong to compact groups or non-compact groups. So unitary irreducible representations of compact and non-compact groups have differences, but we will mention this more tomorrow when we actually talk about building representations. Now the group ISO2 without the reflections is a non-compact group. It seems that in literature, more literature developed of the representation theory of compact groups historically, and then non-compact groups were studied a little bit later, but they have a lot of importance in physics. So this was like a difficult step to take, to consider non-compact groups, but it was something necessary. But so we spent almost an hour just finding the group elements of our two-dimensional Euclidean space. But okay, we use this example to give you all the basic definitions, basic introductions. But you see, it's a little bit takes time. So this is why the rest of the things I will just write out to you what are the transformations instead of finding them. But now you know the main logic, so you can just keep computing these Killing vectors. Now, if you look at Minkowski, so the symmetries here involve spatial rotations, boosts, spatial and temporal translations. Now, spatial rotations and boosts, you may remember, these form the Lorentz group. Now, so the Lorentz group is a subgroup. So spatial rotations is the subgroup of Lorentz group. Boosts is a subgroup of Lorentz group. I think now they have closed commutation relations. Now, Lorentz group, on top of it, equipped with spatial and temporal translations, make up another group, a bigger group. This is called the Poincare group. It's also called the inhomogeneous. Lorentz group. So for D+1 dimensional Minkowski, this is the group ISO 1, D. So for the 4-dimensional Minkowski, this makes ISO 1, 3. Okay, this group is also non-compact because of boosts and translations. And actually, if you want references, Weinberg's book, so Quantum Theory of Fields, Volume 1, Chapter 2. It will take you maybe like a month or two to understand, but it's a good reference. And a little bit different view, like if you want to have a bit different reviews, there's something shorter to read. Although to be able to read something shorter means you have to have thought of it a bit from before. There is lecture notes by Javier and Boulanger. So if you like, this is 4-dimensional. This is more general dimensional Poincare representations. Now let's come to De Sitter. So this was our metric in global coordinates. So the metric that covers everywhere. Here, the symmetries are spatial rotations, spatial translations, dilatations, and special conformal transformations. Now let's compare the two. In both cases, you have spatial rotations and spatial translations. But in one case, you have boosts and time-lag translations. In the other case, these are replaced by dilatations and special conformal transformations. Now, this is another group. This is called the group for DSD+1. This is called the group SO1, D+. Now, this is also non-compact. It is also a Lie group. If you look at it, okay, aside, if you were familiar, let's see, aside, I believe the isometry group of ADSD+1 happens to be SO2, D. Now, all these groups, ISO1, D, SO1, D+1, these are all Lorentz groups, but they're Lorentz groups of different nature. So we always learn about Lorentz group just based on boosts and special rotations, but this is just one example of a bigger family. the most important thing to notice is the lack of time translations. Now, what does this mean? In a practical way, it means there is no global time like killing vector. In a more, how to say, what this leads to is you have to think a little bit about how physics will differ. So this is, for instance, in the beginning, I said, in standard quantum field theory, we learn quantum field theory on flat spacetime, and we have all these techniques of calculating scattering amplitudes. So maybe those calculations, the very technical details of those calculations rely on having these time translation invariants. So here you don't have it. So you will not be calculating scattering amplitudes right away because the machinery for that is not applicable for this on the sitter. So you have to ask, what is the question to ask? What is the thing to calculate now? So that's one thing to keep in mind. Like, this is how to digest this, having different symmetries based on the geometry. But let's stick with more practical things for now. So what does it mean to have no global time?
Can I ask a question?
Yes.
Can you elaborate further the final part? Since I got two questions related to that. Why can't we calculate the scattering amplitude? And instead of that, what are we supposed to calculate? What are our expectations?
Yes, so to calculate, okay, this is more like a discussion now. So let me answer that very quickly. To calculate scattering amplitudes, you need to have you need to build asymptotic states in like early on and later on. And you are not able to do that. So but instead what you calculate are equal time correlators. Let's say one thing to calculate.
But we can build the Fock space, right?
Yes, but yes, you do build those things, but okay, I'm not sure I know what exactly breaks down if you try to do a scattering matrix calculation. Like, you have to sit down and do it to see it, to convince yourself, I think. But some technical things, whatever technical things you could make use of on Minkowski that relied on time translation invariance, you will not be able to make use of here on the sitter. So instead, you calculate correlators of fields at different values, and you can, and these are sandwiched in between vacuum states. This is, in fact, so this is just a 2-point function, but you can put more, like 3-4 point functions. And this is what we wrote down. So what we wrote down yesterday, like, we started with an observation, how Hawking said that the kind of power spectra you needed for structure formation could be obtained as the power spectra of a massless field on the sitter. So this is that is what that was. This is what that was, just calculated in momentum space. But these are the things, the type of things you calculate. And for observational reasons, you calculate these at late times if you want to match it with some observations. Even like you can do all these interaction picture things. Picture calculations. So here you include in time evolution caused by interactions as the way you do in the like quantum mechanics interaction picture. But at the end of the day, you calculate the 2-point function of interaction picture fields, again sandwiched between some vacuum states. And so these are at the same time. They're at different positions in space, but they're at the same time. So you calculate things like this.
I guess since there is no time translation invariance, we are supposed to calculate them at the same time.
Yeah.
Because they also depend on the time, probably.
Yeah. Yes. So this is why these t's are the same t's. Okay. So I hope that helped make a break. But now let's go back to this absence of time translations. Now, a global time-like killing vector would have looked like this. I mean, it will have some constant parameter. So the time component of this will be something constant. So just set it to 1. And all the other angular components will be 0. Now, this is, if you like, this is the solution. But if you look at the killing equations that involve this time component of the killing vector in global coordinates, these are the equations you have. And now, because we don't have too much time, you can try to see if this vector can be a solution to all these equations simultaneously. If you try, okay, so this is automatically solved, very nice. But for instance, this one is not. This bit is 0 because this psi component is 0, but this part is non-zero. So it doesn't solve this, and it doesn't solve some other things. Again, very automatically, this is 0, this is 0, but this is non-zero. So it doesn't solve this either. So this is what it means. You cannot, with this, you do not have this global time translation killing vector as a solution to your killing equations. So to compare, okay, so on Minkowski, we said we have time translation invariance. And here we don't have it. No time translation. But this doesn't mean you worry. It just means you have to understand what is specific to this structure. So the first thing was not to ask or like not to make assumptions based on the Poincare group for what to expect on De Sitter. So you have to teach yourself what this group is, what are its properties, what are its representations, and what kind of questions it applied to this. You know, what are good questions to ask? And we did already discuss. Now, luckily,
Gizem hocam, peki De Sitter Poincare grubunun bir subgrubu değil mi?
Değil işte, farklı gruplar. Poincare grubunun bir subgrubu olarak bu işte boost ve rotational olan Lorentz grubunu bulduk. Çok farklı simetriler bulduk.
Peki temel farkı nedir De Sitter'le Lorentz? Yani tamam, zaman şeyi invariant kalmıyor veya onu bir killing vektör şeklinde yazamıyoruz, değil mi?
Yani elimizde farklı dönüşümler var. Temel farkı bu. O dönüşümlere göre her şeyi ayarlamak gerek.
İşte o dönüşümleri yaparken bir De Sitter'de bir homomorfizma yazamıyor muyuz?
Yazacağız ama Minkowski'de yazdığımız gibi olmayacak. Onu yarın yapacağız.
Tamam, teşekkür ederim.
Gizem, bir şey ekleyebilir miyim? Çok kısa. Özür dilerim. Az eklemek gibi değil de sadece bahsetmek için. Belki sen bahsetmek istersin. Wigner-Inner Contraction'la Poincare grubunun Döster grubuyla bağlı olması.
Ha tabii ya. Öyle şeyler yapılabilir.
Şey ya, hani Inner'ın isminin geçtiği nadir şeylerden biri de matematikte Wigner-Inner Contraction. Ondan sevmek istedim sadece.
Evet evet, teşekkürler. Tabii öyle şeyler var. Daha bir şey söylemek istiyorsan hani bu konuda söyleyebilirsin.
Yok, bölmek istemem ya. Merak eden bakabilir. Wigner-Inner Contraction diye ararsa bağlantılı yani Poincare grubuyla Döster grubu. Matematiksel olarak.
Evet. Okay, one more aside. There is a set of coordinates. Remember yesterday too, we mentioned these just that they exist. We mentioned that there's this coordinates called static patch coordinates. In these coordinates, you do have a time-like killing vector, but these are coordinates that cover one section. So the emphasis is on finding a global time-like killing vector. So you can find a static patch time-like killing vector. But this isn't, how to say, complete enough, you know. This kind of a time-like killing vector, it's not something for the whole of the space-time. So it doesn't save you too much. And as we said yesterday, these are the coordinates for an observer living in the De Sitter era. Now to end with, because we were going to use the planar patch, Poincare patch coordinates, this was okay. So again, okay, one thing to look at. Now let's see what happens if you do a time translation. If you send t to some t a0, this makes the metric come. Now there is this extra piece. So if you do a time translation on its own, there is this extra piece. But if as you do this time translation, you also send the spatial coordinates. If you do the following transformation on the spatial coordinates, so you just multiply them by some constant, then the whole thing remains invariant. This is the same. So time translations alone, again, you see this even in planar patch, are not an isometry, but something that has rescalings is an isometry. In fact, if you do this in, remember we talked about these defining conformal time. Okay, so from here you define a new time coordinate. And in these coordinates, the metric becomes as such. So this eta was from -infinity to 0. In this case, actually what this transformation is, this eta was something like this. So what this transformation is sending eta to H0 eta, and you are sending the spatial directions. You are multiplying the spatial directions by the same amount as well. So this is an isometry, and it looks, it has a bit of a simpler form in terms of this conformal type, but this is what is called dilatations. So this is a subgroup on its own. It's the SO1,1 subgroup, and it just means scaling of coordinates by some parameter. So there's just rename this as lambda. So this has one parameter. And then we wrote on our list special conformal transformations. These are more involved. And in fact, dilatations and special conformal transformations, like all these transformations we're talking about, you already saw them at work in a different setting at yesterday's lecture. Here we are finding these as the isometries of the sitter, but yesterday they were part of what was called the conformal group. They were the important symmetries for conformal field theories. So maybe at this stage, just take this as a hint. It's something to think on, that we are finding these symmetries that are part of conformal field theories here as isometries. And tomorrow we will try to say more about that. But now this last special conformal transformations, they're not so easy to see, but you can think of them as doing an inversion. So this means sending coordinates xi to xi divided by their length. Okay, so you do an inversion, then you do a translation, and then you invert again. This is like these combinations of transformations. And here, this is a 3-parameter transformation. Now, so we have 3 special conformal transformations, 1 dilatation, 3 spatial rotations, and 3 spatial translations for 4-dimensional de Sitter. So all together, we have 10 parameters. So this means 10 symmetries, isometries in 4 dimensions. Now, this is the maximum amount of symmetries you can have in 4 dimensions. There is a way of counting. So in D dimensions, maximum amount of symmetries are calculated as follows. Okay. And for 4 dimensions, this gives 10. So this is why the sitter in the beginning, as we said, is maximally symmetric space-time. Okay, actually, maybe a good point to add that is just to say a bit more about what I said. So we looked at the group SO1, D+1, or for DS4, SO1, 4. So this is the isometry group of DSD+1, but this is also another, this also appears in another way. This also happens to be the conformal group of RD. So Euclidean space in 1 less dimensions than de Sitter. This means...
I'm sorry for the interruption. Just a reminder that we have 5 minutes left.
Yes, yes. Thank you. Thank you so much. So isometry group meant transformations that leave the metric invariant. Conformal group A conformal group means transformations that change the metric up to an overall factor. So it sends meaning to some. Okay, so this is the difference. So this keeps the metric the same. And like, okay, this is also why, because this is the conformal group of something, we came across symmetries that, you know, yesterday you saw that have a place in conformal field theories. Okay, so this is a good place to stop, but mainly what we did today was to just look at the what are the symmetries there for the sitter. And tomorrow we will talk about building their representations.
Thank you so much, Gizem, for this nice talk. Before we start the recording, are there any questions from the audience?
Gizem Hocam, çok özür dilerim ama çok soru sordum. Dilatation'da de Sutter'in bir alt grubu olarak mı ele aldık onu? O daha doğrusu bir konformal dönüşümü yapmak için D+1 boyutu 1'e mi indirdiğimiz için o şekilde dönüşüyor? Yüksek boyuttan daha düşük bir boyuta geçmek için.
Yok ya, bunların hepsi birer alt grup olarak varlar, geliyorlar. Ya biz özellikle boyutları azaltmak için yapmadık. Yani bu böyle bir parametrelik bir grup kendi içinde dilatasyonlar. Bir parametreli, bir jeneratörlü ve bu burada da bir alt grup olarak varlar yani. Yani tam şey oldu mu? Rahat ettirdi mi bu açıklamasını?
Şimdi tabii ilk defa duyduğum için belki ben şey yapmış olabilirim.
Bunların hepsi birer alt grup. De Sitter grubunun birer alt grubu.
Evet. Peki burada D+1 dediğimiz şey spesyal koordinatlar mı?
Yok, tüm toplam.
Toplam. Ama +1 dediğimiz şey zaman boyutu mu? +1 dememizin özelliği.
Hayır, D boyutlu.
Covering page mi? Space mi?
Hayır, bu sadece bir saymaca. D boyutlu bir uzay zamanı barındırabileceği en fazla sayıda simetri bu kadar oluyor.
Anladım.
Bunlar bayağı çarpma toplama.
Küçük bir ekleme yapabilir miyim? Nadir, bu benim string teori grubunda sen vardın sanırım.
Evet.
Şimdi orada bir dakika tam yerini söyleyeceğim. CFT and ADS CFT Basics diye bir dosya koymuştum.
Hocam tam duyamadım. Özür dilerim.
Zaten hani birkaç tane PDF paylaşmışım. Oradan görebilirsin de CFT and ADS CFT Basics diye bir PDF dosyası var.
Evet.
Şimdi onun kaçıncı sayfası? Yani 4. sayfadan itibaren bütün bu maximal symmetric space'lerin izometri grubunun derivation'ı ve bunların nasıl sayıldığı var.
Tamam. Tamam hocam.
Hatta hani çemberle falan başlayarak
Anladım.
Yani bu bir boyut üstten başlamak aslında yani maximal symmetric space generate etmenin pratik bir yolu. Hani uzay zamanımızdan bir üst boyuttan başlayıp böylece yani maksimal simetriyi direkt elde edebiliyoruz.
Anladım.
O dosyadan bakarsan aşağı yukarı anlaşılıyor gibi geliyor bana.
Tamam, teşekkür ederim hocam. Sağ olun.
Okay, thank you so much, Gökhan, for the extra information. Are there any other questions for Gizem? If not, then I'll stop the recording.